Oh, here we go. Can you hear me?
I can. Can you hear me? Can you hear me?
Let's see.
Can you hear me okay?
So I can't hear you. Is your microphone on?
It is. I wonder what's different. Can you hear me now?
Yes, yes. All right, I just had to, I think, so.
What's that?
I think we just had to, I had my speakers.
I just changed my speakers too.
Okay, well, it was one of us.
Can you hear me now?
Yes.
You can?
Yes.
Yeah, I can't hear you.
Oh, no.
How's that? Is that good? Is that good now?
Yes.
Okay, I can hear you too now.
Oh, good. Oh, okay, good. Good. Okay,
Alrighty.
you're a co-host, so you should be able to share your screen.
Let's see. I do not see where I have that ability.
So if you go to the bottom of, like, right underneath the video,
Right?
a little like bar should show up along the bottom, and it says like mute, stop video, and then there should be a share screen option. Oh, let's see. I think I just changed it.
Yeah, it doesn't allow me to
Share.
No. Oh, here it is. Let's try this.
Perfect.
Did that work?
Yeah, that works great.
Alrighty, let's play. Let's play a little bit with the display and see how it runs.
Okay.
All right. Okay, are you? So you see my title slide?
Yep, I see your title slide.
Okay, are people on the webinar only going to be able to hear my voice, or is it audio?
Oh. It's audio and video, so they'll
Right, cool.
see everything, and I'm going to keep them muted and with their video off, and
Yeah.
we have time we can do a Q&A, but just so you know, they won't be like interrupting you or anything.
Yeah, I trimmed it down, so hopefully we have what do we have, 45 minutes, 40 minutes, something like that?
Usually you say like 45 minutes of presentation and then 15 or so minutes Q&A if you want.
Yeah, so I shortened it. I shortened it by probably a third.
Okay.
Because for me, the Q&A is the most fun.
Okay.
You know, get
Today.
repping. Okay, I'm gonna run some animations and see how they work here. Second slide.
Yep, I see the second slide.
Okay. Third slide.
Don't see that. It's on the second still.
Okay. It's a fairly big file. So it still didn't, this should be the fourth slide.
Yeah, all I'm seeing is it's almost like it's stuck on the second one.
Okay.
And it doesn't, it looks like we're not like viewing it as a slideshow. I'm viewing it in PowerPoint.
Really?
Mm-hmm.
All right, so are you seeing it as a slideshow now?
No.
So one thing I can do is so you could run it from there.
Right.
And I can transfer it to you. How about that?
That sounds good. Yeah.
All righty. All righty, so I will go to WeTransfer over here maybe. Yeah, I think the problem is I've got, it's a 50 meg file.
Oh, it's big.
And we've got a small pipe here. We're trying to upgrade to fiber, but I think we're 15 megabits.
Oh, geez.
And I got 100 megabits in and out at home. All right, it's just about. All right, I'll send you the link.
Okay.
I hate this. All right. All righty, so. All right, it should be sent.
Okay, let's see.
How many people do you typically have attending these?
Usually about 30 end up showing up.
All right, did you get the link?
We've not gotten it yet. Let's see if I can.
All right, it got sent.
Let's see, hold on one second. Okay, I don't see it yet. It's probably still trying to send it.
I had another idea. I could I made a PDF version of it.
Okay.
and those are low overhead.
Yeah.
Try that. Okay, here's the PDF version. I'll share. Let's see. Where did it go? There it is. All right, does that? Huh.
Might have to go back and push share screen again. I'm not sure how often you have to do that.
I wonder if I am no longer. Huh. All righty. Here's a Pete. Here it is.
There you go. Oh yeah, that's great.
Is that sharing?
Yes.
All righty. So now let's see if we can. Is it changing?
Yep.
Slide 3,
Yep.
4.
Yes. Yep. I can see your mouse clicking or your arrow clicking the buttons, so that's good.
Nice. All right. That'll be our workaround then.
Cool. Thank you for being flexible about that.
No, no worries.
So I'm just going to do a brief welcome to everybody.
Okay.
And then once you're done, I'll just give them some instructions on how to do the Q&A as best as we can.
Okay.
But yeah, I mean, it'll pretty much just be you the whole time.
Okay.
Let's see here. I'm going to let these people in.
Are you still seeing it okay?
Yes.
Okay.
See it great.
Just in time.
Just in time. For those of you who just joined us, we're going to get started in a little bit. Paul is here. This is Molly. I am at SEFS trying to facilitate this meeting. First time doing this for a SEFS seminar, so we appreciate your patience. And we're hoping to have a Q&A at the end. So, it'll be all based on how we avoid talking over each other. So anyway, please feel free to stay muted, and then we will get started here shortly.
Molly, are you there?
Yes, I'm here.
How is it going on campus today doing the remote classes this week?
I've heard positive things from all the faculty who have been doing it, though some students may be able to weigh in a little bit more accurately about how it's going on their end.
Yeah.
Okay, Paul, I think you can go ahead and get started, and I'll just add people in as they join us. But welcome, Paul, to our virtual SEFS Seminar.
Thanks, Molly. Thanks all for joining me. Today, I'd like to talk about work we've been doing on inland Northwest forests and the relationship of forest successional patchworks to non-forest patchworks. I'd like to begin by acknowledging my co-authors, Miles Lefebvre, Nicholas Povak, and Brian Salter, who also work with me at the PNW Research Station here in Wenatchee. For a long time, we've been studying Northwest landscapes and changes to them, having reconstructed several hundred landscapes now over the last several decades. And one of the things that we've noticed is that an awful lot of forest-capable habitat was in non-forest in the early part of the 20th century. And so today I'm going to tell a story about two projects where we look at the relationship of forests and their non-forests. And we're trying to figure out what the interaction is between forests and non-forests, how the patterns and the processes influence each other. For purposes of this talk, I'm going to talk about non-forest as early-seral and pre-forest conditions, where the patches occur as bare ground, wet and dry meadows, shrublands, sparse woodlands, and savannas, stand initiation or new forest conditions, and mixes of these. And they typically result after fires or other high-severity disturbances. And so here I'm showing examples of what some of those early-seral, pre-forest, and otherwise non-forest conditions look like. And these states can persist for decades to even centuries. And when they're persist for centuries, they're often maintained by fires over a very long time. When they last for short periods, they typically are smaller patches, and when growing on forest-capable ground, they'll often reseed back to forest because the seed rain is nearby and the dispersal gradients are short. Where it takes longer periods, they're typically larger patches, fire touches them more often, and the grass and shrub conditions are refreshed frequently by recurring fires. So one of the things we're finding across the landscapes we're studying is that the grain of these non-forest patchworks matters, and the grain of that larger non-forest context to forest matters. Over the last 30 years, we've reconstructed about 425 early and late 20th century landscapes. And the story of change is probably best shown by these Osborne panoramas that were shot by William Osborne and his associates in the 1930s. And you can see the 20-teen versions of those same photo points. This is a scene looking out from the backside of Mission Ridge ski area near my hometown. This is Mission Peak area, looking into dry mixed conifer forests. And the ridges that are facing us are south-facing ridges and ridge tops. And you can see there was quite a bit of very open and non-forest condition in this dry mixed conifer landscape. This happens to be the Mill Creek drainage. It's the Walla Walla municipal watershed as seen from the Table Rock lookout side. Here we're looking west-southwest. And the aspects that are facing us in the midground there are moist mixed conifer, and the other aspects that are facing more southerly are dry mixed conifer. And you can see that in this watershed in 1935, there was an awful lot of early-seral and shrub and grassland condition, and forests were not the dominant cover in many parts of this watershed. This is in the Eagle Cap Wilderness in the Wallowa Mountains in the 1936 picture.
Hey, Paul.
Yes, sir.
This is John Bucker here. It doesn't look like your slides are advancing on the conference.
Which slide are you seeing?
The title slide.
Wow. Molly, can you see what's going on there? I've shared the screen and it was working before, so I don't know what's going on that end.
I'm not sure if it's just
Yeah, I
me.
see. No, it's not just you. I see it too. It just was working a second ago. Let's see.
I just,
Oh, there's one.
Okay,
How
now
we
we're on
doing?
slide 3.
all right, so you see in slide 2 there?
Yep.
Yep.
Thanks, John, for the heads up. Appreciate
Yeah,
that.
thank you.
Yeah, you bet.
Okay, so here was that slide 2 showing the different kinds of early-seral pre-forest and non-forest resulting after high severity. And the allusion to the short and long periods, small and large patches, and the key is that the grain matters. Can you see slide 3 now?
Yep.
Cool. Okay, so this is that dry mix conifer Osborne panorama comparison showing you pretty extensive early-seral and open conditions in the Mission Peak drainage. This is the Mill Creek drainage, moist mix conifer and dry mix conifer, 1935 to 2019 comparison. This is Eagle Cap Wilderness. This is looking into Cirque Basin, the Macaulay Basin. This is elevation 7,000 to about 9,000 feet. You can see in the above 1936 photo, a mostly wet and dry meadow dominated basin filled in with lodgepole pine and subalpine fir and spruce in the bottom one in a period of decades. And here's Slate Peak. This is eastern Washington, northwest of Mazama. You can see within this 120-degree panorama, widespread early-seral conditions resulting after mixed and high severity disturbances. And the period is 1934 to 2013 in this comparison. So what I want to talk about here is non-forest in forest landscapes. How abundant was it? How patterned? How important is it? How does it vary by province? And we're also asking if there are changes in the modern era. And what is the potential role of non-forest and changes in non-forest in the landscape ecology of fire in the adjacent forest? And to do that, we're comparing early 20th, late 20th, and early 21st century conditions to get some notion of the trends across time. And we've done it for a number of provinces. And here today, I'm just going to show 4 comparisons that I think are instructive. But before I do, I want to sort of tell you where this sort of line of thought came from. Susan Pritchard's lab and mine and Penny Morgan's, we recently completed a GFSP project where we were looking at the effect of reburns over space and time. And in this particular project, we were asked to, hopefully you're able to see the slides in my cursor here. We were asked to evaluate 3 different burned areas. One in northeastern Washington, the Tripod burn area, the Cascade Complex in Idaho, and another fire complex in British Columbia. I'll use the Tripod area to illustrate. These black dots that you can see here are all the ignitions that occurred from 1940 to 2005, the year before the Tripod fire ignited. And in this project, we were basically going to ask the question, if we had done management differently, if we'd allowed some or all of those ignitions to burn, considering their antecedent weather conditions and then the fire weather that drove those fires hourly and daily, what sort of landscape would the Tripod ignition have met in 2006? To do that, we developed a new kind of state and transition model, and that state and transition model is it's a run wild kind of state and transition model. Basically, annual fuel succession and forest succession is driven by fire, annual ignitions and burns that move through the landscape if their energy release component is sufficient to allow fire. And fuel succession and forest succession then are an emergent property of reburning. And if you look at the state and transition model, we have a no fire rack on the top here, and then we have low, moderate, and high severity fires that are reburns that allow transitions to occur in surface and canopy fuels as a consequence of reburning. The map on the left side is essentially a map of the pathway groups or the biophysical settings where dry mixed conifer, moist mixed conifer, cold, moist, and cold dry forests would occur. And so for each one of these, there is a state and transition model. And I refer you to our JFSP report and a couple of other papers if you're interested in that work more deeply. But the real point of introducing this work is to say that we started seeing when we would run these combinations of ignitions and antecedent weather curing conditions and then fire weather, we started seeing a strong interaction between the area and contagion of complex forest and the non-forest that would result as a consequence of burning. So I'm going to window in now. This previous slide is 3,000 years of allowing these simulations and interactions of ignitions across pathway groups to burn over space and time. And then here's a windowing in on just 1 millennium of burning. And what I want you to notice is that old forest multi-story is this dark blue here, and you can see it in the trace here in the cold dry forest, and you can see it in this example of dry mixed conifer forest. What we noticed was when young multi-story forest in the dark green and old multi-story forest and occasionally understory reinitiation, these are fully forested, full canopy cover, often complexly layered late successional forest, when the contagion and the abundance of that condition increased to a certain level, what we would see is ignitions, provided they had the right kind of fire weather, would produce quite extensive areas of non-forest, which you can see here is post-fire bare ground, and then in pink here, the stand initiation or new forest structure. And so what we saw was this sort of dance going on between, at very large landscape scales, the amount of complex forest and non-forest that would emerge as a consequence of forest regrowing after prior ignitions, increasing in contagion, increasing in ladder fuels and that sort of thing, and then interacting with ignitions. And so that led us to want to go back to some of our Columbia Basin data sets and ask the question, well, how much non-forest was there and what was its role? What's really going on in this dance between forest and non-forest? And I want to sort of set the stage by talking about why I think this can be important. We now know that landscape resilience is hierarchically structured. There's fine, mesoscale, and broad patchworks or textures that are interactive, and there's crosstalk between these different scales. We know that wildfires are processes that maintain these dynamic patchworks of burned and recovering vegetation. And we further know that some of the burn scars, they spatially interrupt fire flow while others facilitate it. They interrupt it while fuels have basically been consumed and there's not much that's available to burn. And they facilitate it when they're flashy fuels, and they're some of the first that have availability to burn. And so we see that there's these feedbacks that are influential to whether fires are more or less frequent, they're large or small, or where they're high or low severity as a consequence of this crosstalk between these scales of conditions. And so one of the questions we're trying to ask with the non-forest work is to say, how extensive are these non-forest conditions and what's their role on the landscape? And can the role change? For example, how often do alternative stable, these non-forest states, typically occur? And are they just simply, are alternative stable states common as dirt? Are they an outgrowth of forest fire ecology? Is there one kind of model, or are there many kind of models of these forest and non-forest relationships? And that is to say, is there significant geographic variation? And then finally, we want to ask the question, is this information useful in the context of climate change? Can we understand something important about how forests and non-forests will change as the region warms and gets drier? So to move forward with that work, we went back into our Columbia Basin data set where we had photo interpreted early and late 20th century conditions. These white watersheds are sampled watersheds within these provinces. The aerial photos representing the earliest conditions were the 1930s to 50s. Typically 30s and 40s were the most common. And the late 20th century is represented by photos from the 1990s. And then to represent the early 21st century, went into the landfire data set, looking at 3 different layers that we use to build early and mid and late seral forest conditions, combined between the environmental site potential, existing vegetation cover, and the vegetation height layers from 2016 refresh. And the results from the Northern Cascades and the Southern Cascades and the Upper Klamath and the Blue Mountains are what I'm going to spend some time and attention on next. So we're looking at the Northern Cascades, and here is a plot of early seral conditions. And what we've done in this particular look is used the potential vegetation type, which was photo interpreted as the most shade tolerant vegetation species present in either the early or late 20th century photo interpretation. And so here is ponderosa pine in the lower left corner. You can see the percentage of area represented by the ponderosa pine PVT. It's smaller than in the Northern Cascades. It's a fringe type dry mixed conifer. You can see there it's dry ponderosa pine, Douglas fir in the driest grand fir settings, about 10% of the province. Moist mixed conifer, some of the wetter pine, Doug fir and grand fir moving into the larch with Douglas fir. And then some of the dry cold forest, moist cold forest. These are lodgepole pine or mixes with subalpine fir, Engelmann spruce in mixed or pure type. And the other forest PVTs are represented by silver fir and noble fir and western hemlock red cedar and those kinds of things. And urban shrub are basically true herb shrub types where they are not forest capable. Non-vegetated is rock, water, ice, anthropogenic types, that sort of thing. And so on the lower left, you can see the percentage of the provincial area. And I want to focus some attention here on the proportion of the early 20th ponderosa pine. It represents a small area, but what we found was that most of the pine potential vegetation type was in a sparse woodland. It was such a low tree density that it would be better defined as a woodland or a savanna type. You could see that that was true of most of that area. When we check the soils for those same areas, what we see is that they were mollisols formed in a grass fire regime. When we look in the dry mix conifer, we see that there was much less early seral condition in the early and late 20th century, and that's increased quite a bit in the early 21st. Moist mix conifer, similar story. The green line shows you 50% of the PVT area, and over here it's the percent of the total provincial area. So this right bar plot here shows you very modest change from the early to late 20th century, and then a little more significant change in the early 21st century, mostly influenced by the dry, moist mixed conifer, dry and moist cold forests. When we look at the tabular data, we can see the proportion of early seral versus mid and late seral by these same conditions. And you can see that the North Cascades was sort of a 40-60 province, about 40% of the area, even though the majority of acres is forest capable in watersheds that have at least 50% forest cover in them. You can see that there was a small change early to late 20th century in the amount of early seral, but it's actually changed fairly significantly from a 40-60 to a 60-40 early to mid plus late condition. And most of the changes occurred in the dry and the moist mixed conifer and in the cold forest conditions. When we look at the Southern Cascades, the changes are a little bit more significant. You can see that This was if you look at the amount of early-seral in the early 20th century, you see that most of it was mid and late-seral forest condition. It increased as a consequence of harvest in the late 20th century. You can see that manifest in the pine, which is actually a fairly extensive type in the Southern Cascades. More than a third of the land area is in this dry ponderosa pine type. And you can see that early-seral conditions increased as a consequence, typically of harvesting in the late 20th century, but they really increased quite significantly in the early 21st century. So you can see that as a percent of province here on the right side, and you can see the contributing PVT areas that are influential to those changes. And we described the Southern Cascades as sort of a 25-75 province, really forest capable. A great abundance of the acres that are capable of growing forest are growing forest when we find them in the early 20th. Harvesting influences that in the late 20th century, and wildfire has flipped those conditions in the early 21st century to something more like a 75-25 province. When we look at the Upper Klamath, we see a very, very different condition. We see that early-seral forest conditions in the early 20th were really quite common. That is, an awful lot of the forest capable acres were actually maintained in grassland, shrubland, sparse woodland. When we find them early in the 20th, that condition decreased. We actually see forest encroachment on early-seral forest conditions. And then in the early 21st, we actually see a return to something like the abundance of early-seral in the early 20th century. And this is a look at the tabular data. It was a 75-25 sort of province, and it's actually moving back towards that sort of condition, with early-seral being a little bit more abundant, and that's actually influenced by the potential vegetation types you see in the green boxes in the early 21st century there. And finally, the Blue Mountains, this province here, you can see that there was a fairly significant amount. This is a sort of a 50-50 province where the early-seral condition was really quite common in the early 20th. In the late 20th century, we see that a little bit more common, but we see it really scaling up in the early 21st century, again in these drier types and in the cold forests as well. When we look at the tabular data, we see this 50-50 province moving to something more like the Klamath, where there's sort of an unprecedented amount of early-seral condition in comparison to the mid and late-seral condition, contributed mainly by these encircled potential vegetation types. So fairly uncharacteristic for the early 20th century look. On the next step, we wanted to basically say, so what? What does it matter? How are these changing? And so we, instead of looking by PVT, we basically dissolved back to just non-forest patch sizes. And in this exercise, we're asking the question, if we compare at a province scale the patch size distributions for these 4 provinces, and we set them on an equal footing. So the 4 hectares was the minimum map unit for the photo interpreted data. We made that equivalent across all 3 data sets. We're not using PVT, we're just looking at non-forest patch sizes. And what we're doing now is we're saying, are the patch size distributions shifting? And what's the direction of change, if any? And to do that, we fit 1 parameter power law models to probability density functions of log-log transformed cumulative distribution functions for the non-forest patches. And then we compared the slopes of those 1 parameter P1 models using maximum likelihood estimation with goodness of fit testing, where we ran 2,500 different Monte Carlo iterations to see whether or not the models fit well and the differences were significant. And this question we're asking here is really pretty simple. Is the contribution of the smaller and the larger patches changing? And is that having an influence on the grain of the landscape? So just to refresh your memory here, when we compare the slopes, the shape parameter of the power law model, what we're really asking is, has the change in the patch size distribution when you fit a power law model to the log-log transform data, what is the slope and what does the slope tell you about the change in patch size distribution? In blue here, you can see that the absolute value of 1, when that slope is close to 1, that indicates equal contribution of the smaller and larger patches. When it's greater than 1, that indicates that the smaller patches are contributing more to the pattern. And when it's less than 1, the larger patterns are contributing more. And the simple question is, are these relationships shifting? And we found some surprises in the shifts compared to the PVT data, and that's what I'm going to show next here. So, showing you 3 things here. We unpack the data on non-forest patches using patch sizes that are sort of characteristic of the way we view fine and meso and sort of large patches. And this is something like sort of a log normal binning of patches. And in the left panel, we're seeing the percentage of patches by patch size. And in the middle, we're seeing the proportion of the total area that is represented by patches of the same sizes. And then in the right, we're looking at the P1 model fits and changes in the slope parameter. And one of the things you can see when we look at the Northern Cascades is that between the early 20th and the 21st century, those patch size distributions have shifted to the right, indicated by a flattening of the slope, and the largest patches in the right tail are almost an order of magnitude, a little bit more than an order of magnitude larger than they were in the early 20th. When we look at the Southern Cascades, we see an even broader shift when we look at those same data. And you can see that there's a significant change in the contribution in the left panel of the largest patches to the shape of the patch size distribution. So that tips us off that we should be seeing this kind of relationship in the middle graph and this kind of relationship when we compare the shape parameters of the power law models, more than a 1 order of magnitude increase in the influence of the largest patches. The Upper Klamath is really alternative to this. We see no significant changes. If you look at the percentage of the patches by patch size, what you basically see is large patches were influential on that early 20th and late 20th landscape, and there are not significant changes in the shape parameter of the non-forest patch size distributions. And finally, when we go to the Blue Mountains, we see that this 50-50 province is more influenced now by the percentage of the patches that are large, and it's tipping the distribution, flattening that slope a little bit in an uncharacteristic way. So, to summarize, the way we're thinking about these forest and non-forest interactions is that we think the non-forest conditions are a vital context to forest. We think that there's this dance going on from the data that we're looking at between forest and non-forest. These shifting patch mosaics are not only shifting forest successional patchworks, but they're moving through alternative states, which can be short or long-lived. And the non-forest context, we feel, is critical. In some situations, non-forest is more abundant on forest-capable settings than is forest. The Klamath, Upper Klamath, is a good example of that. Whereas the Southern Cascades seems like it's an area, because of its environmental settings, its climatic conditions, was capable of growing more forest on those forest-capable settings. But in each case, there's this unique geographic interplay between ignition frequency, fire weather, and forest area with high canopy cover and complex layering. And the way we're thinking about it in terms of our reburn modeling and now in these reconstructions is that there's a tug-of-war going on between factors that are growing forests and those that are removing forests. Another way of thinking about it is forests may in fact vary in how much potential energy that they can store as forest. And we think that this might be some of what we're seeing in the geographic variation that appears to be apparent. And that suggests to us that if, as a consequence of environmental settings and regional climate, there's variability in this non-forest-forest relationship, that it's likely these conditions are in flux with changes in the climate and in fire weather. Another way of saying it is that the grain of the non-forest probably matters. And we think that it's changing from relatively fine to meso to somewhat a more coarse grain. And we think that that's probably a fairly important thing. When we look at the grain of the Blue Mountains and the Cascades, what we see is this sort of fine to meso grain where the majority of the patches are smallish, and they have the ability, as a consequence of processes like regeneration and seed dispersal, of being dynamic elements on the landscape. They're non-forest for the time, they're encroached and they become forest again. But it's more difficult for larger patches to become forested again, and there's a couple of things working against them. One of them is it's more difficult to keep them from being touched by fire again and again and again. Those grasses and shrubs cure out the earliest and they stay cured the longest. And so if a large patch is touched by ignitions, it's more likely to be reburned rather than a small patch. And it's less likely to be more rapidly reforested than a small patch. So this forest non-forest interplay, we think, from our results so far, gives us clues also to what we might expect with climate change. And this is where we're going in our future work with the reburn modeling. Our hypothesis is that with warmer and drier conditions, we should expect less forested area and less area with high canopy cover, so more open forest conditions. And that likewise in cooler and moisture conditions, we should expect that forested area will increase as our conditions with higher canopy cover and layering more complex forest. Regardless of whether the climate is cooler or moister or warmer and drier, what we are seeing is forests are seldom at their carrying capacity. That is, all of the acres, or sometimes even most of the acres that are capable of producing forest, are actually growing forest at any one time. And we think that that is because of this tug of war of factors that's going on between factors growing forests and factors taking them away. And that's what we're pursuing with our reburn modeling going forward. Revisiting this plot again, the reason we built the reburn model is that it allows us to be able to find out where historical patterns and variation came from when you allow structure to become an emergent property of interacting fires over space and time. And that gives us the ability to say, if we now seed in ignitions with the increased frequency of these 98th and 99th percentile fire weather events and their accompanying meteorology to support fires burn period by burn period, should we expect to see changes in the relationships that were more typical historically? And so that's the thing that we're pursuing as we go forward with our reburn modeling. How am I doing, Molly, for time? Do I have time for questions?
Yes, plenty of time for questions.
Nice.
So what I will say is, you all have probably done this in your classes, but just try not to talk over each other, and but feel free to unmute yourselves and ask your questions.
That didn't work.
That's why you don't.
Hello.
Okay, sorry about that. Just some technical difficulties. Okay, go ahead if anyone has any questions.
Paul, I'll start. This is John Bucker.
Hey, John.
Hey, that was really interesting. I was curious about two things here. I guess the one I'll focus on is your second last slide. You had the millennium in your reburn model that you were looking through there.
Yeah.
And you mentioned emergent properties, and it looked like there was quite a bit of synchrony here. Right? You've got the yellow in this dry mixed conifer. It looks like it's hitting a peak every 125 years or something.
Yeah.
Is that a consequence of your modeling, or is that one of those emergent properties?
It's one of the emergent properties. One of the things that we're finding out is the neighborhood of your pathway group is influenced by how different vegetation types, their rates of growth and fuel fall down are influenced by the ignition. So sometimes we see moist mixed conifer exhibiting the fire regime of the dry if it's highly interdigitated with it.
Mm-hmm.
The same is true when we see cold forest interdigitated with dry forest. We see that there's crosstalk between the pathway groups. So one of the things that is demystifying for us, John, is this idea that potential vegetation types have a fire regime. What we're finding out is that neighborhood effects are really consequential in this model. So, so they help explain why we see structures emerge that in cold forest that look like they should be associated with a lower severity fire regime.
Mm-hmm.
Things like that. So yes, there's crosstalk between these pathway groups and how they burn, and you will see synchrony when large scale weather. So in the reburn model, we're actually using the actual meteorological conditions that cured the fuels and then would have pushed the fire had it not been put out.
Okay, yeah. So, so is that a neighborhood matters? Does it matter, do you think, more than PVT, or like what would be the relative importance of neighborhood compared to PVT? Have you tried to quantify that?
We haven't yet. It's a really good question. You see a neighbor or a PVT kinds of effects being important where you have less extreme fire weather, but where you have more extreme fire weather, you see departures in what would be ordinary for the PVT or the pathway group.
Sure, sure.
So that one of the bottom lines is we see low, moderate, and high severity fire in every type, and neighborhood effects matter to that, and there's tremendous crosstalk. Basically, when you get above 94th or 95th percentile fire weather, you get quite a bit of crosstalk between pathway groups in fire regime, and that will for a time synchronize what can happen regardless of the pathway group until you see, in the absence of ignitions, more environmental conditions taking hold within that pathway group. So
it's overriding it at that point.
It's overriding it for a time, and then you see it go back into a more characteristic condition unless extreme events happen to be back to back or populating across a large landscape. So, and one of the things that's pretty neat about this is when we go back and check our work to see whether or not the fire size distributions we're getting from a model that's being run essentially by FS Pro simulations, we're getting very characteristic fire size distributions as an emergent property of these interacting ignitions. So
cool.
We feel like we're getting good behavior with it, and there's some real surprises, as we've just discussed a handful of them that are part of it. So
that's really neat.
Yeah, thanks, John.
Yeah.
Hey, Paul, this is Brian Harvey, even though my screen says Denise, I think, but.
Hey, Brian, how are you?
I'm good. Hey, just wanted to say, really fascinating talk and cool to see. I've seen earlier iterations of this and heard you talk about it. So I think it's a really profound example of the importance of two landscapes having the same proportion, but really key differences in configuration.
Yeah.
Just a really awesome example of that. And so related to that, a question that I had on this slide that you have up here is, have you looked at how these trajectories play out in terms of those patch size distributions? Because it would be interesting to see, you know, there, like John was just saying, the synchrony here, or periodicity in the spikes in these things, if there's a decoupling with how the patch size distributions of those things are occurring through time. Just thinking about that in terms of how it functionally plays into this as an emergent property.
Yeah, it's a really great question. It's one of the next places that we're going, Brian. We spent the last year and a half doing a calibration that surprised us that we needed it. But John, it's one of these properties that you get to when you're allowing your model to have run wild properties. For example, we found that there's a lot of old forest that's stored in small heterogeneous patch sizes that we missed in our Columbia Basin work because we had to have a minimum map unit to finish photo interpreting 7 million acres twice, because most of the patches are small, right? And so we had this minimum map unit, but what we're finding out is old multi and old single story occurs in really fine textures as well. And these are 90-meter simulations, pixels, for this large area. And so we had to do two things: figure out whether or not that was an artifact in our model or it's a real thing. And what we're finding out is it's a real thing. And the second thing we needed to do was figure out how to age out old forest, single story, that would be a collector on the landscape, because it's difficult to show stand replacement by high frequency fire in the way that fire scars will sculpt out and cause tree collapse and that sort of thing in these frequent fire systems. So we added that feature to this particular model. And now that allows us, Brian, to go and address your particular question, where we can now start increasing the frequency density of different fire events by their antecedent weather and by the extreme nature of their fire weather, and find out how they reshape patch size distributions over space and time. And so getting to the point where we could actually start to exercise that component has taken us about a year and a half. And we're super excited about now generating patch size distributions that we can take into the MLE work that I just showed you, and see how we can expect climate change to morph patch size distributions and so forth on the landscape.
Awesome. Yeah, thanks for sharing this with us.
Yeah, you bet.
Hey, it's Alina.
Hey, Alina.
How you doing?
I'm good. How are you doing?
Pretty good. So I have a question for you about how your modeling's constrained by the state in transition models, and also might inform things like what's built into land fire. And just to preface this, my work that I've done in really high elevation forests has made me think what's described both in books and land fire describes a much higher severity fire regime up high than we actually see on the landscape.
Yeah.
And so I'm wondering, like, if some of your fire regimes, like, could there be misparameterization of the fire regime in the beginning, or alternatively, can your modeling feed back to what's stated about some of these areas and inform us about what the regime actually should be?
So I have to tell you, Alina, I think that our understanding of the fire ecology of some of these higher elevation cold forests is really going through a metamorphosis right now. When I looked at a lot of high elevation cold forests in the early 20th century data sets, I found things that I couldn't explain from simple high severity fire regimes. And once we started getting really high def 1930s panoramas that we could zoom in on, we started seeing the effects of low and moderate severity fires in lodgepole pine, in subalpine fir, as a consequence of the dominant part of many of these landscapes being wet and dry meadows, where you're seeing low energy release, short flame lengths lap at thin bark trees and not having a stand replacement influence. That's one of the reasons I showed you that Macaulay Basin photo. And it's not trivial, it's not uncommon. So my sense is that there's a relationship between these meadow and shrub field connections to cold forests that really are going to reshape our thinking about the broadness and the variability of cold forest fire regimes. I think it's not separate from the non-forest ecology in the surrounding area. And it's one of the reasons we're trying to do a deep dive in it. I think that some of the HRV simulations that we get out of the Landfire Project are a tautology. They take assumptions about the way we think the world works, and they put them into a state and transition model that's altogether shaped by the initial parameterization set that you provide to it. It's one of the reasons why we wanted to build a model you didn't do that to, where you literally got structure as an emergent property of fires that were being pushed by antecedent weather and weather during the burn. And we were hopeful over a 5-year development period that this would allow us to be able to find out the dynamics that produce the variability we were observing, but then ask the question, if the forcing factors change, can we expect anything like the past to occur in the future? And our sense is nothing like the past is going to occur in the future in many of these landscapes.
I think that gets at the question. Thanks, Paul.
Does
We'll
it?
talk more. Yeah, it does actually. So, yeah.
How are we doing for time, Molly? We good?
Doing good. If anyone has any other questions, we have a little bit of time. Otherwise, you know, good whenever you're good.
Looks like Sean Dorr had a question that came up in the chat. I don't know if you can see that, Paul.
Let's see.
I can see it. Can you see it, Paul?
I'm not seeing it.
Okay, I can read it to you.
Yeah, please.
It says, what's your definition of, quote, characteristic conditions? Why did you start at the early 20th century, and why not start 20,000 years ago?
I'm interested in understanding pattern and process interactions for a climate that's similar to the one I'm in, and forest conditions that are similar to the conditions that we're in. I'm interested in understanding, in the case of fire, is a major shaping process, how the variability that emerged as a consequence of different fire severities produced variable structure across the landscape. And then I want to ask a question going forward in shorter time spans: how can mid and late 21st century climate influence those conditions, given what I have in the landscape now and what I might have had 100 years ago or 200 years ago? So while I'm interested in the paleo ecology, something more proximate is more interesting to the questions I'm asking right now.
Hey, Paul, it's Kayla.
Hey, Kayla.
Hi.
How you doing?
Good. And I'm glad to hear you're well and everything.
Yeah.
Hear all these familiar voices on this thread. I was kind of stunned by your results for the Blue Mountains and the flip-flop in forest to non-forest there. And just briefly talk about what you'd say to collaborative groups that are looking at doing thinning projects that are looking at manipulating the forest structure in that environment, given what you've shown us.
So is your reference, Kala, to scale and scales that matter, or what specifically about that do you want me to unpack?
You know, there's something wrong with my connection, and the sound is really distorted, so I didn't hear your last question.
What part of that do you want me to unpack relative to the collaborative?
Oh, yeah. That you've got so much. You've got 80% early-seral versus 17 today, whereas in the past you had more of a 50-50 split. And it might, somebody might look at that and think, oh my gosh, our forest conditions are so rare, let's not touch them, especially if the early-seral is going to be delivering a lower intensity flame. I'm not sure about that, but
Yeah. Well, so your question is, how can Blue Forest or Blue Mountains collaboratives be more successful? That kind of thing?
sure.
Yeah. I don't know. I think an awful lot of the treatments right now in the Blue Mountains are about getting a harvest volume obtained, and rather than creating, patterns that that are going to motivate the processes and the scales of processes, they're interested in going forward. And so I think one of the things I would do is to get to basics and ask them about where they want to go, and what do they think is going to help them get there, and is it going to be just going and thinning the acres where you can cover your base rates and get a volume, or do you want to restore something that's more characteristic and maybe even a little bit more resistant to some of the coming changes? And so far, those conversations, they haven't evolved. They're trying to, but they haven't evolved. So.
Got ya. Thanks.
Paul, this is John again. I've got another question, which is I was really struck by how dramatic the change was from late 20th to early 21st century. It's not
Which
a long
one?
time period. From your mid-Columbia Basin work to 2016.
Yeah.
Right, that's a 20-year period,
Mm-hmm.
and how little change there was between the early 20th and late 20th century. And I'm curious what you think is maybe it's a thought question. What would you expect if you were looking at something in the mid 20th century, like somewhere in the middle of that range? So, 1980, where do you expect it would have fallen then, and how dramatically or how rapidly can this change over time?
Good question. I don't have the mid 20th data, but if I were to surmise, I would say that you would have had increasing early-seral in small patch cuts and sort of staggered setting harvest units. And in our results, basically from the Columbia Basin assessment, said that you steadily got more and more fragmentation as a consequence of selection cutting and regen cutting. And so it was really changing the grain of that landscape as a consequence of management. And then in the mid 20th century, we were still in a pretty cool, moist climate, and fire suppression was marvelously successful. And so I think an awful lot of the primary influences were management influences over that time. An awful lot of the climate change data supports the period since 2000 to the present day, the last 20 years, as producing an uncharacteristically large amount of large, high severity fires.
So would you point to that as a climate change signal then?
Absolutely.
That'd be really interesting.
I would, excuse me?
I was just gonna say, it'd be really interesting to look 20 years previous and say, here's what it was like in the 30s, here's what it was like in the 80s, 2000, 2016, and see that progression.
It would. It would. It's pretty expensive data to obtain from the PI work.
Sure.
We were fortunate. I think we probably got 15 million into the PI work alone to get to this place. But the question you ask is a really good one. Some of the literature, John, that influences my thinking is the idea that over the last 20 years, our suppression machine has become incredibly effective at extinguishing fires that are basically less than 97th, 96th percentile weather events. And the ones that are escaping initial attack are the ones that grow big fast, and they're either happening under extreme fire weather or in moderately extreme fire weather where we're completely resource limited, so fires just get big.
Yeah.
And my sense is that's what's operating since 2000. And when we look at we did this analysis with the MTBS data, and I presented that work at IALI and AFI conferences, and it shows a very similar thing, that the larger fires that are getting away are the ones that are escaping initial attack, and they're occurring under more extreme conditions, and also when we're resource limited, because regionally fire suppression resources are limited. Everybody's deployed.
And of course, those extreme conditions are not so extreme anymore.
That's exactly right. And so for us, asking the question, if you start seeding in extreme fire weather events at the predicted frequency under different emission scenarios, what does that landscape look like? And are there conformations of the landscape that are more robust, more resistant against more extreme effects? My sense is we'll see area burned continuously increase, as is predicted, but we may be able to influence with some configurations and disposition of fuels the spatial pattern of severity. It's an open question, and it's one we want to explore and see whether or not there's opportunity there.
Cool. Thank you.
Yeah, I think there's a big climate change influence here, and it's interacting with fuels and declining suppression efficacy. And it seems to me that that's going to continue. So,
Although I guess if it was a climate change signal writ large, you would see it consistently in all of these provinces.
Yeah, unless the province's wiring, like in the Upper Klamath, is to have a high degree of grassland, chaparral, that sort of thing. You know, looking in the Upper Klamath and finding out that it was ordinary for it to have so much of this grass, shrub, sparse woodland condition was an ordinary circumstance when we run into it in the early 20th century. And to see it going back, Nick Pavek and I just submitted a paper where we're basically showing the same thing throughout the rest of the Klamath in California. It's a big fire-driven system. It was, it is, it will be.
Cool.
In fact, the power law model only fits to the right tail of the Klamath province in California.
Oh, really?
Yep.
It's Kayla again. It'd be really interesting to look at the character of that non-forest in the Upper Klamath, because there is some suggestion that the shrubs have gotten so tall that either they're going to intersect with the tree canopies, or they're not going to carry mixed severity fire the way they used to. And one of the things that might be happening on that landscape is that it's so easy to suppress fires that they're suppressing any climate signal in the increase in area burned. But at some point they may reach a threshold where they can't contain it anymore, and then it'll just explode, maybe.
Yeah, I think all good points. I think that they're actually potentially reaching that threshold right now with the transition we're seeing from the late 20th to the early 21st. I had to be honest, I was very surprised when I looked at the Klamath and looked, basically dissolved out the potential vegetation type, just looked at non-forest patches to see literally no significant change in the power law fits. So essentially, it looks to us at a province scale that the patch size distributions are resuming their former condition, just as a consequence of fires thus far, Kala. So it'll be interesting to see with the old growth chaparral in many of those conditions, whether that just continues to wink out forest.
Paul, this is Brian again with a follow-up question to that about the patch size distribution, at least for the Klamath, matching up at the province scale. I was curious if you've been able to think about this, or if it's even possible with this data set to think about those patch size distributions at a series of nested scales to see where there's any decoupling across those spatial scales potentially.
It's a really good question. It's a place we want to go. we want to look at scale-wise effects. And there's only one data set, obviously, that we can do that with, and that would be the land fire data set, where we're sampling watersheds. We maintained the PVT polygons and the sub-watershed sample areas consistent throughout these 3 looks, so we wouldn't introduce that artifact. But the question you ask is a really good one. I would love to see wall-to-wall coverages of vegetation, which, as we know, are not available for the timeframes we're interested in, except in the more recent era. But we also want to see whether or not there are scale-wise effects in the modern wall-to-wall coverages. So we're going to look at that as well.
Okay.
Do you have, Brian, do you have any handle on earlier wall-to-wall data sets that might work for a question like that?
I wish.
Okay, as long as we have no other questions, I think that about wraps it up. Thank you so much, Paul, for being here, and for everybody attending, for doing this virtually. We may end up doing this in the future, regardless of COVID. So
yeah, well, thanks for being here and for the great questions. I appreciate the chance to share some of our work. Stay healthy, folks.
thanks all.
Thanks, Paul.
All right, bye.
Thank you, Paul.
Yep, bye.